unmute. There we go. Okay, so let's do some announcements for today. That way we can spend 5 minutes. Okay, let's see. Where is the pen? The pen is here. Darn. Okay. Hate when I forget to switch the mode to the short latency. Anyway. Okay, so we have a few things to talk about. One should be homework 2, which, I promised last Tuesday, or this Tuesday. And I see a lot of conversation about it. And, of course, I didn't do. It's just unbelievably busy all the time. I always think that I'll have an extra 6 hours per day that I don't have, so I just end up having to push things back. I pushed it back to, and of course my friend's messaging me on Steam as soon as I start teaching. Why does he do that every single time? Gotta close Steam. Okay. So I'm gonna try to get it out today. I'm gonna try today. I'm gonna do my best. So supposedly the exam, I think, is gonna be next week. Exam 1 maybe next week. Yeah, no, I mean, I keep my cell phone basically dead now all the time. I don't even have it ring anymore since it's 95% junk calls. I don't know if you guys have those as much as I do. I get maybe 10 or 20 junk calls for every real call I get. Yeah, so that's kind of the real important thing. It's going to be a take-home, obviously. It's not going to be on Blackboard. I think I'm going to make it something like maybe, it should be maybe around 10 questions. And mostly it's going to be, maybe 5 of them are going to be more like math type analysis. And 5 of them are going to be like drawing. So for instance, what I mean by drawing is like, what should I say about drawing? It's basically like if you have like a, some kind of AVL tree, like, and I'll draw you an AVL tree, something like, I guess this might be an AVL tree. Let's see. Heights here are 3. The heights here is 2. So I think this works. And I say insert, 5, and then insert 10, and then insert 15, right? And that could be a problem. So basically, and then I could make some drawing problems where you. So basically, the drawing are going to be insertion, deletion. From like AVL, splay, and red black. It's I might ask some questions about cues, so I might make you draw out a cue. Well, math analysis means probably at least 2 induction problems, maybe at least. So the thing about induction is that it's a method of solving a problem, right? So the thing about induction is not that you should never think like, oh, this is purely an induction problem, even though you should basically usually think like, oh, this is the best way to solve it. And in a lot of cases for tree analysis, it's definitely the best way to solve it. So, you know, I'll try to figure out a way to make some problems that are, I'll make some problems that I hope are both, you know, interesting, interesting, maybe enlightening. But obviously not too bad. I don't want them to be, you know, graduate level proofs that you need, you know, really advanced stuff for. I just want, you know, basic. So yeah, you can print the exam, you can do whatever, and then you basically I want a PDF submission. On Blackboard. So that's what I want. And I guess in terms of, yeah, I think this is generally the format. You know what I'll do is, I think, let me see if I have my exam from last semester. Let me see if I can pull that up. So let me see what I have under practice exam 1. And then maybe I'll pick out what I have under the actual exam. Do I have the actual exam here? Yes, I do. Here it is. So, yeah, I mean, maybe I'll just send this out. Yeah, sure. Let's see. What's the best way? I guess I can post it on Discord, maybe. That's probably the easiest way to just upload files in the next like 10 to 20 seconds. And you can just look at them. You'll have some idea of, maybe I should rename this exam from previous semester. Practice. Well, since it's a take-home exam, you're going to have a full week, right? So I'm going to assign it maybe Monday, and it'll be due on the Friday, or maybe I'll even something like that, right? So you'll have at least a week. And I think I wrote up some solutions to it, didn't I? Yeah, I did. At least for the practice exam, not the actual exam. I think I just went over the actual exam solutions in class. So I'll just upload these as well. Okay. Okay. So the exam these exams were supposed to be completed, at least I don't know about the practice exam since that was given, you know, as a practice, but the actual exam was completed in 75 minutes, so hopefully I'll make it, I mean, I assume that you guys are going to take a lot longer on the exam at home because you'll have a lot more time to focus on it, but anyway. Okay, so there you go. That's all the stuff. I'll probably post that as an announcement on Blackboard for the people who don't check Discord regularly, but anyway, so that's generally what we do this in terms of exams. Exams are a hard thing to do in the online format. It's definitely, there's not a lot of perfection going on. So okay. So okay, so let's talk a little bit let's just go over one last time red-black deletion. So let's just talk about it one last time, and then we can go into heaps. So maybe I'll spend about 15 minutes on this. I don't want to spend too much time on it, but basically I want to give you an overall rundown of the algorithm. So, and I know that all the cases are a bit confusing, so let's just talk about the cases and talk about how we determine what to do. So basically, here's a tree, and so here's where you start. And so here is, I guess I could even draw it in this way. So if the node we're deleting is red, you just delete it. So that's a good thing. So if the node is red, then we just delete it, right? So basically the red-black deletion is very simple in that case. On the other hand, if the node is black, then the problem is that it could have, it could have a red parent and some red children. So if you just deleted it, you could end up relinking. Well, I guess is it a leaf node? It could be. Well, it's a leaf node with no successor, right? Or it's a node with no successor. So technically, I guess it could have a predecessor that's red, and so when you relink the predecessor with the node up top here, you could end up relinking a red node. So this is the problem case. This is what we're really worried about, is that if we ended up deleting this node and relinking these two things, if you ended up doing this, then you would end up relinking. And the other problem is that, so that's one problem that we could end up with. The other problem is that what we're doing is we're taking the black height at BH, and we're taking it down to BH minus 1 by removing this node, right? So basically, we're upsetting the height of the tree. Okay, so what are the cases now? So basically the easiest case, which is why it's listed under as case 1, is when the sibling is red. So when the sibling is red, basically what you're going to do is you rotate the sibling up to the parent, and then you recolor everything black. Or I'm sorry, wrong case. So if the sibling is red, you do rotate it up to the parent, but you leave the parent. You leave the former parent red. So let's do that. So basically here, now if the sibling is red, you rotate up to parent, and you basically swap parent and sibling color. So this is what you do in this case. And so now we're in the other case where the sibling is black. So as you notice, this is not actually a red-black tree. This is a tree about red-black trees, right? So this is like a flow chart almost, right? So if the node is black, then we have to go down this path, and then if the sibling is red, we rotate that up to the parent and swap the color. And then if the sibling is black, so this was case 1 here, right? And so this is cases 2 to 4, right? 2, 3, and 4. And so basically the cases for 2, 3, and 4 are just different subcases of where the sibling is black. And so what can happen in each one of those cases? So basically if the sibling has 2 black children, then we're in case 2. And so remember what you do if you're in the case 2, which is this case where we don't know what the parent color is. Does that affect root? What do you mean, does that affect root? Oh, of course, yeah. So if you swap the color and the color of the parent, well, I guess the thing is that yeah. So this might affect the root, and then if the thing is the root, you have to recolor it black, right? So basically, at the end, no matter what you do, you always have to go like tree dot root, is equal to dot color is black. Yeah. So I mean, everything affects the root, and it's totally possible that one of these recoloring operations is going to recolor the root black. Red. But the trick is that once you recolor the root red, even if it causes some other problems, like its children are red or something else is going on, just recolor it black, because that's that's like rule 2 for the binaries, the red black tree. So you don't basically have to like worry about that after you've. Okay, so both of Sib's children are black. And so then what this is this is a case 2, right? So what you do in a case 2 is you push basically in a case 2, there's only really 2 options. You basically push the extra black token that's accumulated on X up to X dot P. You don't do any rotation, you just push the extra black token up. So one of 2 things can happen in that case, right? If you push the extra black token up and it's red, then basically the black token supersedes the red token and this node becomes black, right? So in the case where the parent is red, then let's see here, what have I done? Right, so you push the black color up to the parent, and we're cool. If the parent is black, then the problem is that when you shifted this extra color up, then the problem is that this one has an extra black token, and you have to keep doing it. So basically, yeah. So case 2 is you shift extra black to parent, sibling to red, and then you set x equals x dot parent, and you redo. So then this is the recursive case. This is the case where you have to check the parent. So, yep. Okay, so then case 3, right? So basically, case 3 is this case. Sort of, yeah. So X will start out. So X starts out is the node being deleted. So I think the first time that you run it on it, if the node being, so it's possible, so the node being deleted is always like basically usually a leaf node, right? So if we're deleting some kind of leaf node with no children, or I guess it has no successor, so it could have a predecessor, and then we have to rejoin, then the thing is that, like, technically that node becomes null pointer, but you can basically just pretend that it's still there for a second, and just run the operation on it. So let's see what I named as case 3. So what I named as case 3 is that the right child is red. So we're in this condition. So we have black, and here's X, and the sibling is black, but the right child. So the left child is black, and the right child is red. So this is case 3 here. And it's better just to draw it than even to talk about it, right? This is case 3. Because like this is case 2, right? So case 2 here is where you have a black node, here's X, here's the parent, here's this, and then you have 2 black nodes there. And the end result condition for this is that you shift, so let's just draw it with an extra black ring on X, so there's like 2 black rings on X. The way to draw it now is that there might be an extra black ring on the parent. It could be that the parent was red, so maybe I should draw a little red ring in here, so the parent could also be red, right? So it depends on what happens here. You have to check at the parent. And then here, the node is black, the sibling became red, and its 2 children stayed black. So this is the result of case 2. And so then the result of case 3, because remember that this node can be a null pointer, right? So I think what we're going to have to do, if I don't forget case 3 correctly, we'll probably have to rotate and then swap some colors, right? So we'll rotate the sibling up. So we'll rotate the sibling up like this. So now this is the sibling, this is the parent. Technically this is X down here. And then here's the one child, and then here is the old red child, like this. And then what we're going to have to do is some kind of recoloring. So what does it tell us to do in terms of recoloring for case 3? It tells us to recolor everything black. So there we go. So cool. And then of course there's case 4. And case 4 is this thing here. Oh, so how firmly should you be able to grasp this? I think the way I understand it is that I wrote this diagram for myself here, and I wrote this recently, and before that I really did not have a very firm grasp on the algorithm. And once I wrote this, now I have a pretty good understanding of how it works, in the sense that, like, if the node is red, you delete it. If the node is black, you have to do something. If the sibling is red, you do the, case 1 thing. If the sibling is black, then you basically look at the children. The children are either black or there's one of them that's red at least, and so you go from there. And so kind of the idea here is that, like, at every point, it kind of makes more and more sense once you draw it all out. But honestly, like, I remember when I took data structures, we didn't have to, we never actually had to do red-black deletion on any exams. And there's a reason for that. I mean, now that the exam is take-home, I guess I could technically allow you to do some of that, and that would be more okay. Just because you would be able to use, like, all of your, tools. You could even use the visualization, right? So you could actually see what the true answer is. So the problem is not just going to be delete it, it's going to be explain why this deletion doesn't break the black heights, right? So that's unfortunately... So the good news is you're not actually going to have to invoke the algorithm without my diagram and without the visualization. The bad news is that you're probably going to have to explain what it's doing. And so you'll have to actually draw in, like, which black height is at which node, and then just make sure that as the rotations and as the red-black recolorings happen, the black heights don't get messed up, and you never have a red child of a red parent. At least that's what I'm currently thinking about this kind of thing. If I even do red-black deletion, Whoops. Haha. No. So, there we are. And then, okay. And so, in this case, what you're going to do is so you want to make this into a case 3, right? So basically what you do, So the BH minus 1, right, so, well, let me explain what I mean by that. So, well, actually, let's just do some more visualization stuff once I talk about case 4. Let me just get through this, and then we'll talk about the black heights again. So case 4, you see, we don't know the color of the parent. We have this. So what we're going to do is we're going to exchange the colors here. And the reason why we know we can exchange the colors is because this one's black, and this one's, sorry, the sibling's going to be black, the right's going to be black, so we can exchange the color here, and then we can rotate. So once we rotate, then we see that we're in a case 3 again, because we have a right red child, we have a black sibling of the node that's either being deleted or the current node on the way back up with the fix-up process, right? So X can either be the leaf node that we're deleting, or it can be the place in the fix-up process as we're heading back up the tree, which is why technically we're not really messing too much with X, because X can have black children, red children. There's a lot of things that X can have. The only thing we know about it is that it's a tree of black height BH minus 1, because we've just deleted a black node, right? Otherwise, if we had just deleted a red node, we just delete the red node and stop, right? So if we're doing any of these cases, we know we've only deleted a black node. So by deleting the black node, we know that it's messed up the black heights. We assume that we fixed up the black heights in this subtree, so that basically if this has subtrees, this is BH minus 2, and this is BH minus 2. So we assume that the black heights are fixed up until here. But over on this side, the problem is that once we've deleted the black node from this side, this one becomes heavier in terms of the black height. And so we have to do some extra work to fix this up, right? So that's kind of the explanation here. And so what we do, I guess, in case 4 is you swap the colors. So you swap colors like this. So you say doot, 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 doot. And then let me draw something in red. So you swap these colors like this. And then you rotate so that you actually rotate this person up, right? So it actually, so this is, I'll name this right, no, that's left. That's left. So I'll name this L, name this right, name this sibling, parent, X. And then here, X stays, parent stays. I guess parent could technically be red, but parent stays. And then we get left, left, and then the sibling, which is red here. And then we get the right node all the way down there. And so this is what we get. And then you see, wait a second, so technically this could also have a subtree here that got rotated up, right? So now there's a new right node here. And now you notice that this is actually a case 3 again. So basically case 4 is really just like case 3C. It's the case where we have one red child, the red child isn't in the right position, it's in the left position. Really, I shouldn't say right and left. Really what this means is, I mean, you look at this and you say, this is the, like, zig, right? This is like the zig condition, and this is a zigzag, right? If you're thinking of it as, splay trees or whatever, then you notice that this is in the like the L position, the alternating. This is the, like, the right left versus left right versus, you know, this is in the right position or left position. So this is the straight position, and this is in, like, the bent position, right? So that's the distinction between these two cases. So if you do the reflective thing, then you shouldn't be talking about rights and lefts. You should be talking about the fact that, like, this node is the straight line condition and this node is the bent condition, right? So I don't care if you have the same tree like this, except this is the node you're deleting if this is X, and this is the sibling now, and then here is the red node, right? And here is the black node. You'd be like, wait a second, but now the one on the right is still the sibling's right child is blah blah blah, you know? But no, right? So the point is always, like, you look at what the symmetric case is here. And so this is the zigzag condition. So because this is the zigzag condition, this is also a case 4, right? And the same thing with the left position. So if you had something where, this was all identical except flipped over, where this was on the right, and now this subtree is on the left, that's still a case 3. And so, as it turns out, when you think about this, does this handle every possible case, right? And the answer is yes, because, you basically go through and you say, well, if the node is red, yep, okay, cool, the node can be red. And now if the node is black, then the sibling can be red, and we resolve it that way. If the sibling is black, then there's 3 different ways to resolve it, but are these all the different ways you can resolve it, right? So I guess technically this node here might be red. It's either black or red, I guess. So, so the point here is that if both the children are black, you do the case 2. If the inline child is red, you do case 3. And if the out-of-line child is red, you do case 4. And that's really good, right? Like, it does encounter all the possibilities. Everything is done. So I think this is a decent diagram of the situation. I'm not saying it's not complicated, right? So if you're saying to yourself, like, man, if I had to code this with no notes, no memory, I'd basically, like, just die immediately. I agree. This is not something that you want to do without a lot of, like, of support from textbooks and references and all kinds of stuff, right? And maybe even a functional red black tree to look at. So the reason why I made my little diagram is because I want to show you what the algorithms book does. So I want you to see how they handle this stuff. So here's, let's see if I can pull up the deletion. So here is their deletion stuff for their cases. Instead of coloring them red and black, they color them, the black nodes are the black nodes. The lightly shaded ones are red nodes, and then the slightly more shaded ones are either red or black. And this is not at all confusing, right? If you're going to do this, you have to spend the money and color the nodes red and black. You cannot do this in black and white. And so this is what Corman does. And then what does our algorithms book do, right? Let's see, data structures in C++. Here it is. So our red-black algorithm does it this way, where they color the nodes very slightly. I don't know if you have even the slightest inability to sense, this is blue, which is red, this is black. Okay, now figure this out, right? I mean, this is awful coloring. Like, look at this. Doesn't that give you just a little bit of, like, a headache? You're like, oh my god. The little slightly blue nodes that are dark blue are red nodes. They didn't color them red, they colored them light, or very dark blue. Almost indistinguishable. Almost indistinguishable. No, I mean, this is garbage, right? I mean, like, I'm not saying that their explanations are bad. I'm not even saying that their diagrams are wrong. I'm just saying, look at that and try to picture it. Understand what they're doing. And it's difficult, because you have to look really carefully and be like, oh, 15 right here, right? So this is a red node here, this is a red node here. Like, okay, I understand now, because if we counted the black heights, like, that kind of stuff. I don't know. And so, here is my diagrams, right? I'm not going to say they're perfect. I would like these two triangles to have a bit more separation. I would like, but here's the thing. What I did was, and I know it's huge, right? But what I did was, I did diagram, and then I did explanation, right? And then I did a diagram, and then I did the explanation for that diagram, and then I did a diagram, and then I did the explanation for that diagram. And that's all I did in this thing, right? That's what I did. And so, and I made sure all the red nodes were red and all the black nodes are black, and any node that's undetermined is split red-black, right? Oh yeah, and I made the current node, I gave it a little gold-yellow circle around it. So, I mean, you know, yeah, blue and red. No, I mean, like, I get that, like, it doesn't matter if it's a blue-black tree or a red-black tree or a green-red tree or whatever you want to do, but you gotta make those colors distinguishable in your book, right? Otherwise, it's just gonna be undistinguishable garbage, right? You just can't see the difference. Anyway. So that's my opinion. And so if you're wondering, why did he write up his own and not just use someone else's, I searched around on the internet and I found some of them which were better, but like I never found anything that was like this. And even this isn't perfect, but this is, I would say, better. I would say that this is better. Yeah, I mean, I think one of the things is that maybe a lot of the authors themselves don't really want to write up the red-black deletion part, so they just don't put a lot of effort into it, maybe. Well, who are you going to sue? Are you going to sue me? I mean, I don't know. Okay, so you want to talk about heaps now? Let's talk about heaps. Okay? So, if you thought red-black deletion was hard, get ready for heaps. Heaps are going to be just, you know. So what's a heap? A heap is a full and complete. Well, I shouldn't say that. It's it's at least full. And I'll explain what I mean by full. Binary tree. And the rule, so notice I did not say binary search tree. It is a not equals to search. Okay? So the rule for a heap is that the parent is dot value is bigger than any of the children dot values. And that's the rule. So a heap is not something that you use for searching, and I'll show you why. A heap is something that you use for finding the maximum. So it's part of what we call priority queues. So you know what a queue is, right? So a queue, whoops, come on. All right, I'm gonna erase this crap because that's just awful. Okay. Right, a queue is something where you get in line, and here's the front, I guess, and here's where you enter, right? Enter the queue. And so if you get in line, you go here, and here's the front of the queue, so then if we take the next person, we go here, and now the front is here, right? And then if you put someone else in the queue, they go, 2 more people in the queue, they go here, and then the next person gets removed from the queue, and you put them up, and then the front becomes there, right? So that's what a queue is. Well, you notice in life, there's always people who get to skip the line. It's like that thing about a club, right? Where, people can skip the rope line, or alternatively, basically, like if you're in a hospital, right? Technically, the hospital waiting room is supposed to be a priority queue, right? If you come in with a bloody nose, they'll sort you to the end of the queue. But if you come in with like a rod, a metal rod through an organ, they'll be like, that's probably higher priority, so we'll put you up towards the front. And so, anyway, so the idea is that a priority queue is like a queue, right? Basically, it's like first in, first out, except people with higher priorities go first. So really, it's not really FIFO anymore. So it's not FIFO anymore. It's really highest priority, right? Highest priority first out. That's what it is. HPFO, hypefo or something, right? So, let's just do some examples of this. Let me show you the kind of model that we build in our heads of what a heap is. So let's say that we insert the element, say, 10, and then let me build a heap like this. So 5, 2, 4, 3, 1, and we can even have another priority 1. So this is a heap. We can even have something like this. Let's say 2 and 1. Okay. So you might be asking yourself, like, okay, cool, but do the siblings relate to each other in any way? And the answer is no. So there's no sibling relation. No sibling relation here. And what I mean by that is that if you remember the relation for a binary search tree, right? So for a BST, when we put the S in there, we know that the x dot left is less than x, which is less than x dot right. And this might have an equal sign on it, maybe. Right? So, yeah, so this is a BT, not a BST. Right? The search condition is where if it goes left or right. But, yeah, exactly. So, well, in a binary search tree, there are relations between siblings, right? Because the left sibling has to be less than the right sibling. So, but in a heap, there are no relations between the siblings, right? And I kind of did this basically in every case. Well, I guess we could make this too. So this one looks like a binary search tree relation, but it isn't, right? It doesn't care. It could have been 2, 1 or 1, 2. It doesn't matter. Here I put 5 in the left child just to emphasize the fact that this is not a binary search tree. I put 4 in the left child to emphasize this, 2 in the left child, not a binary search tree. Okay, so now here's the question, right? What if we wanted to insert a node? So let me insert a new node. And so you might be like, well, how did you know where to put it? The answer is you always make this a full tree. And what I mean by a full tree is that basically every level is filled. So except for the bottom level, except the bottom, which is filled left to right. Okay? So the only insertion requirement is that the thing is a full tree. Okay? So basically, you know exactly where the thing has to go now, because the next node that gets inserted is going to get stuck here, the next node that gets inserted is going to get stuck there, etc., here, there, etc. So, let's just insert a value, instead of just putting all these blue nodes down here. Let's insert one value and see what happens. So, I'm going to insert 7, to which you immediately say, hey, wait, that violates the heap condition, right? Yep, right? So when we insert 7, that violates the heap condition. So what do we do in that case, right? So we make the tree, yeah, basically, well, it's even more than just balanced. So it's entirely a full tree up here. So it has every single level populated as full as possible, except for the last level, which populates from left to right. So yeah, it's basically as equally balanced as you can make a tree. I guess it's as equally balanced as you can make a tree, except for the last row. Let's just say yes. So the point is that what the operation here is not rotation, okay? So rotation preserves the binary search property. That's the whole point of rotation. But here, this is not a binary search tree in the first place. So actually we can do something even simpler. Can anyone think of how to fix the relation between 3 and 7 here, right? And what's the problem here? It's that the max always has to be the parent, right? Max is always parent. And technically, I should have said that this is a max heap, right? So this is a max heap. Could you build a min heap by the exact opposite property? Yes, but let's just assume that right now we're just building a max heap, only max. So how do we fix this property here? How do we fix this? Yeah, so actually, that's right. All you have to do here is just swap these two values. So a 3 goes in here, and a 7 goes in here, right? And then you say, wait a second, now it violates the property here. Well, swap them again, right? Swap them again. So now we have 5 sitting here, and we have 7 sitting here. And then all we have to do is we have to compare it versus its parent, right? And now we say, okay, it's less than its parent, so it'll stay down here. So there's one slight problem, which is actually not a problem, but it's a slight concern, right? If this is the first time you've seen heaps, you might be like, yeah, I get all that, that's fine. But what guarantees me, right? What's my guarantee that that this is bigger than this other side, right? Right? What if this were 8 here? You know, what if? And we don't want to go searching down in this side of the tree. So what if this were 8? So what if this were 8? Ah, yes, exactly. You see, that's the thing that saves us here. It was impossible that this was 8. Right, exactly. So it couldn't have been that way, right? It can't be that way because if this were 8 and this was 5 to start, remember that this was 5 when we started, then if this was 8, then this would have already violated the heap property and we would have already broken our heap. So this would not be a heap that we were inserting to. And so the good news is that, like, if it's already not a heap, the swap operations, you don't care, right? It can break, it doesn't matter, right? What we're assuming, like when you insert into an AVL tree, when you insert into a red-black tree, when you insert into a binary search tree, when you insert into a max heap, you always assume that the thing you had before was actually the correct data structure. If it's not the correct data structure when you insert, you know, who cares what it does on the way back up, right? But if this, so the maximum that this could possibly have, this had to be less than or equal to 5, and so because this was bigger than 5, it's okay to swap, and we know that because we swapped this one down, do heaps have a parent? So if you implement a heap in this way, yes. So, okay. And so let's do one more insertion example at least. So let's insert the value 4 into here, right? So you stick a 4 in here. Now, of course, your question is, how the heck do I know exactly which way to follow the tree down, as in a parent pointer? So, yes, if you implement it this way. But I'll show you a way to implement heaps in just a minute that doesn't use pointers at all, or maybe one pointer. So, okay. So, here what we have is a 4 here. And so this, actually, this purple thing, this is okay. It doesn't, right, violate the heap condition. And so what do we do here, right? What do we do to purple? And the answer is nothing. So I don't know. I haven't seen the heap project yet. I don't think it's been written yet, so I don't know. Anyway, so, okay. Now, all of this is well and good, right? All of this is perfect. Except one thing, right? What's the problem? I've taught you how to insert, right? And I told you that you're never actually going to have to find, right? There's no heap find algorithm. And the reason why there's no heap find algorithm is because, say I tell you that I'm searching for 1, right? So, anyway, so I want you to think about this, right? Why can't we search for 1? And the answer is because if I tell you, okay, my left child is 7, my right child is 2. I mean, let's fix the tree here and make this say 0, right? So you think, oh, maybe I'll just go to the one that's closer, right? It's more likely that I'll find a 1 if I go down the 2 path than it is if I go down the 7 path. Well, no, because I've just changed this to 0. So here, the point is that you look at this and you say, wait, there's no 1s in this subtree. So, okay, cool. So you can't go down the one that's closer. Can you go down the bigger tree? I guess, but then how would you decide which way to go here? Would you just have to search everything? The answer is actually just you have to search everything, right? If you want to do find in a heap, at least this type of heap, you have to search everything, because it's possible that you'll be able to find the value, or it's possible that you won't find the value. And, so if you go down this path, there's no guarantee that you're going to find a 1 down here. This could have been a 2. It could have been a 0, right? If you go down this path, there's no guarantee you're going to find the right answer, even if it's in the tree, right? So basically, in order to do it, you basically have to do a full traversal of the tree. Like, I don't care if it's pre-order, post-order, in-order. You have to do some kind of traversal of this tree and search every node to find something. So find in a heap is O of n, where n is the number of nodes. So that's kind of bad, right? Insert, on the other hand, because this is such a well-balanced tree, is always O of log n. But the good news here is that if you're using a heap, generally you're not running the find algorithm. Okay, so the point of a heap is not to run the find algorithm. The point of a heap is to have 2 operations, and one of them is insert, right? So one is insert, and one of them is like pop, or delete max, or get max. Right? I don't care what you call it. If you call it pop, if you call it delete max, if you call it get max, whatever you call it, basically, and how expensive is finding the max? So find max is really cheap in a heap, right? It's really cheap. And the reason why it's really cheap is because to find the maximum, and say we're not deleting the maximum, right? So we've done insert, so we know how to insert, that's log n. We know how to do, well, we don't know how to do this one yet. We'll figure that one out in just a second. But how do we do a find max operation on a heap, right? And then you say like, oh, well the max is just sitting right up here. So you basically just do like root, dot value, and you return that, right? And so you're like, oh, yeah, this is O of 1 here, right? Nice. This is the real advantage to a heap. The heap, now, of course, if you remove the max, then you might have to do some extra work. But if you just want to find the max, it's an O of 1 operation. And doesn't that sound nice? Right? That's pretty nice. Pretty good. Pretty good. Do any of you watch the hydraulic press channel on YouTube? Just out of curiosity. Okay. So I filled up this slide with garbage. So let's do a new slide. Say 10, 3, well, that's not, well, whatever. 2, 1, 8, 6, 4, something like that. So, oh, when they were popular, ooh, that's a burn. Oh, and let me just add in maybe 1 here, and maybe a node with a 0 in here, and then like, I don't know, like another 0. So, okay. So now it's time, right? There comes a time in anyone's life where you have to talk about delete max. Right? And now's that time for us. We have to talk about delete max. So what you want to do for delete max is you want to delete that 10, right? But we need to preserve the heap property. So what are we going to do? Right? So the idea here is what we're going to do is we're actually going to delete the last node that we've inserted. And we're going to copy that value up to the root. And immediately you say, so what we do is we delete, you copy last node value to root. And then you delete last node. Well, yeah, I'm sorry, he was a good boy, but he's gone now. So now what do we do, right? So now we're in a situation where basically what you usually do is you check, right? You say, is this guy bigger than this one and this one? And the answer is no. He's 0 is less than both of them. So this is way out of position, right? So here's what you do. You take the maximum of the children, right? You can't take the minimum of the children. You take the maximum of the children and you swap, right? So here what we're going to do is now we're going to swap down. Wouldn't it always be smaller? The answer is generally yes. I mean, I guess if you insert things with all the same priority. And can heaps be in reverse where the least value is on top? Yep, that's called, right, that's called a min heap. So basically the only difference between a min heap and a max heap is the direction of the alligator, right? The direction of the inequality. So that's why, in general, when we teach this stuff, we only talk about max heaps. We don't talk about min heaps, and the only reason is just to avoid some confusion, right? We don't want to be like, oh, and then you find the min, and then you find the max, and then you find the min, and then you find the max. No, we just say find the max. If you want to find min, you just reverse all the inequalities, and then everything works identically. So at this point you say, okay, is this bigger than its children? And the answer is yes. So you pick the maximum, remember, always the maximum child, and then you, so this will be 6 here, and this will be 0 here. And so you notice that actually 3, you find the max of the children, and 3, terrible. 3, you swap, right? And then you find the max of the children, and you swap. You find the max of the children, and you swap. Now, if if the maximum of the children is less than this node, so let me do, let's see here. Let's do an example where that's the case. So let's say we have something where we have maybe, I don't know, 8, 3, 2, 1, 5, and then 5, right? So let's say 2, 1, 1, 0, 4. This is kind of annoying, isn't it? And then we can have, say, 5 here, which is what I want, 3, and maybe 2. No, we don't want any of those extra nodes. We want, this is what we want. We couldn't recursively shift the greater value side up, so you don't have to keep track of the last value inserted. The problem if you do that is that you don't know what the last node you're going to take is. So for instance, if we go back to our previous tree, that's an interesting way to say it. Yeah, I mean, I'm not the absolute worst. So, what I really should say is that I'm not at the bottom of the max heap. So, yeah, so that's the problem, is that what it would do is that if you always shifted up from like the lowest side here, what you would do in this case is you would shift, like say that this were 0, whoops. You would say that this was 0 and this was 1. Then what you would do in this case is that you would end up shifting, well, I guess you would shift this one up, and then you would shift this one up, right? And so the problem is what that would end up doing for you is it would suck up this node, and you'd have to delete this node. But then this is no longer a full tree, so it breaks, like, fullness. It's not a bad idea, and I've had that idea before. And I thought, like, can you make it work? Can you, like, then once you break the fullness, could you then just shift this node into that position? I think you might be able to, but then you might have to swap it back up anyway. So, yeah, so I, unfortunately, that doesn't work. You know what the sad fact is? That I think that was actually a previous student. Very sad. So anyway, okay. All right, so let's deal with deletion here. And so this is the reason why I say that you might not always have to swap. So if you delete, what you're going to do is you're going to kill off this 5, and you're going to stick 5 into here, right? And 8 comes out, right? 8 is returned. So 5 goes in here. And then you check and you see, like, what's going on, and you say, am I bigger than my children? And the answer is actually, I am bigger than or equal to this child here. And I'm also bigger than or equal to, well, I should say, I'm also bigger than or equal to this child, right? So in that case, you don't actually have to continue the swapping process, so you can stop. But I guess this is a little bit of an edge case in the sense that, like, you see that I had to kind of construct this thing very carefully to make sure that we didn't have to do any swap operations. But I don't know, you know, that's how it works. So, okay. Yeah. So any questions about any of this? So, right, remember, I'm always taking off, when you insert, you're always inserting from the left to right in the last row. When you're deleting, you go backwards, right? And then if you delete this node, then you would go here, right? And this would be the next node to delete. Yeah, so basically whatever the last node is that was inserted is the first node to get deleted. So insertion goes left to right, deletion goes right to left. Okay, any other questions about anything here? So I think next time I will cover, yeah, there's no rotations here, no rotations. If we're going to do leftist heaps, and with leftist heaps, there's an interesting thing that you can do where, if you notice, you can actually swap left and right children. And if you think, oh, thanks. So if you notice, you can actually select what would have happened if, well, let's just delete 0. Sure, let's do it. So you delete 0, you put 0 up here, and then you basically swap down for the max. So let's swap down for the max. Let's swap down. So what we're going to do is we'll say, okay, now 0 is in here, whoops, and 5 is in here. And then we swap down one more time. So remember, you're always going in the max direction, and the reason why is because when you pull the max up, you know that it's at least bigger than the other side, right? Okay. Yeah, so that's basically how deletion works. Let's just keep deleting. So if we delete this one, nah, it wasn't Prof J. So the thing is, here you swap this one up here, so you'll get 5 and 1, and then you have to swap the 4 up, so then you get 4 and 1. And then, of course, here, if we delete again, so let's delete one more time, or let's delete a few more times. So when we put the 1 up here, and then we have to swap for the max, so we notice that the max is over here, so we're going to swap the 4 up to the root, and then we will swap the 1 down here. Let's make them blue now. And then if we delete the 2, right, so we're going to delete the 2, or I should actually say what we do is we delete the 4, the 2 comes up, right, and then we swap for the max, and now remember the max isn't this way anymore, the max is this way, so now what we're going to do is we're going to swap up. So, yep, we're going to swap up 3, 2. And now, if you delete one more time, right, and then this will end class, but if you delete one more time, right, we already deleted from right to left as much as we can. Now you have to go up and start deleting from this row. So you stick a 1 in here, and then you shift it down towards the max. So here what you do is you say 2, 1, and then finally you shift one more time. You say 2, 1. That's right. So as you insert and you delete, and so basically that's how you do it, right? You just insert from, you insert in the binary search tree trying to make it as full as possible, and you delete by keeping it as full as possible, right? Because if you take off the last node, it's still a full tree. Delete the last node, it's still a full tree, etc., etc. And then when you get to the end of the row, you just go back to the next row and work your way to the start. Now, if you implemented this as a tree, it's actually kind of hard to implement this particular deletion and insertion method. But if you implement this as an array, it's actually way easier. And so next time on Tuesday, I will show you how to do that. Okay? And I'll show you how to do an array, and then we might talk a little bit about maybe leftist heaps. So we're going to do more heap stuff. And then we might talk about some really fun stuff like binomial heaps and Fibonacci heaps. So those actually were mega confusing to me because they were taught to me in a kind of weird way. But I actually think I have a decent explanation that lets students, so at least my first year teaching, I was able to get students to do binomial heaps and Fibonacci heaps without too much problem. So, and basically that all has to do with the idea of binary addition. So if you know how to add two binary numbers together, you can do binomial and Fibonacci heaps. Anyway, that's all I have for you today. Hopefully you vaguely understand red-black deletion. I'm not hoping that, my goal is not to get you to be able to do it from memory. My goal is that you sort of understood the process well enough to be able to basically, like, you know, explain it as it's happening or something like that, if you know what I mean. So, okay. All right. Cool. I'll let you go. Outro time.